Prova, prova. Well, I guess. Can you hear me? Yeah. Okay. Well.
So our next speaker is Alessandro Georgoudis, who is going to tell us about hexagons and small spin to strong coupling.
Okay, well, first I would like to thank the organizers for inviting me. It's always nice to be in London, beautiful place. And I will talk about some recent work done with Benjamin Bassot, which is in the audience. And it is based on some a bit more ancient work done again with Benjamin and Artur, which is a PhD student at ENS. Anyway, let me start actually in the same way as Frank did, which is by saying how good is actually computing, that we can compute the spectrum in n=4, and how this is one of the great success of integrability. What does it mean? Well, as Frank very nicely said and introduced for me, is the fact that using the quantum spectral curve, which is some mathematical tool that can give us a different, the value of the anomalous dimension for a single trace operators in the large n limit in n=4 at different values of the coupling. And this is a truly fantastic tool. I would suggest you to go download the implementation by Dima and try to play with it for perturbative. It's very fun. And you can insert whatever you want, and this will spit you out practically the anomalous dimension for operators. This is, for example, I think the 11-loop anomalous dimension for the Konishi. Of course, you can also go through finite coupling and compute the anomalous dimension, again, for the Konishi at different values of the coupling. You see interpolation from the weak to the very strong. I think this is some old, as there are way more nicer end result. And of course, you can also go to the strong regime in an analytic way. And this is some new result made by Simon and Kolya and Paul, where they actually were able to compute the Konishi anomalous dimension up to 1/λ⁴ in the strong coupling. So this is fantastic. This is the spectrum. And as we heard, what can we do about the structure constant? Well, most of the results that we've seen are focused on computing the Konishi structure constant, which is super important, but one would like to push further. And of course, as we have seen, different methods exist, and there is no unified, at least we don't have a very good unified picture for all of this. So the result, as we've seen, it's practically the perturbative computation was done using Feynman integrals, and it's still stuck at 5 loops. Hopefully someone will try to push it higher. And we've seen from the talk of Frank that there is this boosterability framework that works extremely well, where we can have some interpolation between weak and strong coupling, where we get very good bounds. And this is some sort of a middle ground between the small. And of course, we can also study the strong coupling expansion as has been done through this analytical bootstrap or this ADS Virasoro-Shapiro amplitude, of which we'll hear about tomorrow by Shai and Maria. And we've seen that we can go through very small setup of anomalous dimension. We can go through all these stages, but we need to use different tools. So what can integrability give us that can interpolate between all these things? Well, there is something, which is this hexagon proposal that we heard from Benjamin in the first day, and from Frank briefly in the previous talk. And the hope is that this object, or some modification of this object, will give us something that we can actually use between these 3 different regimes in the same way that the QSC does for the anomalous dimension. Of course, this is a dream, as I will try to show that we have almost good control over the small spin, the small coupling, but finite coupling is still complicated. And the aim of this talk is to try and show you that actually we can do some things as strong coupling by learning some lessons from the anomalous dimension. Okay, very well. So let us start and jump into the single slide about the hexagons, and I hope it will be clear enough how they work. Very well. So I was a bit sketchy by saying what actually structure constant we care of. So in principle, we would like to care about structure constant of multiple spinning operators and things which are very nice and complicated. Unfortunately, they're too difficult. There are some results by Carlos, Pedro, and other people where they try to compute the spinning 3-point function from OPE of higher point function and hexagons. Very nice, but unfortunately, it's very difficult to push this forward. So we will focus on a very particular setup, which is practically a very reduced sector. So n=4 in the planar limit has a huge symmetry, and we will only focus on what is known as the SL2 sector, which is somehow like a simpler subsector of the whole theory, where we only care about operators which are built up by Litecoin derivatives and some complexified scalar combination. So the numbers that appear here will be important, so let me focus on them. So the spin of the operator is identified by the power of the derivative, and then the length of this operator is connected to this twist of the operator. And we have, of course, I would like to do spinning. I can't, so I need to reduce to actually try and do this protected half BPS operator. So this will be my playground for today. So I'm only caring about this sort of structure constant. It would be nice to extend, but it's very difficult. OK, let me present what is this hexagon proposal for computing structure constant. Can be pictorially represented in this way. So the idea is practically you take a 3-point function represented in this way. We have the non-protected operator on the top, and then we have the 2 protected operator at the bottom. And the idea is that I can cut through these different seams, and I can construct a more fundamental object that, as we've seen from the talk of Benjamin, can actually be used also for constructing higher point function through what is known as hexagonalization. So this building block I can bootstrap using integrability, and it has some form which, OK, will be important, and we'll present it later. But for now, I just wanted to understand how, reconstructing the full structure constant works. So I can build up these 2 objects, think of them as some sort of form factor amplitude, and then I need to glue them back together to reconstruct the starting 3-point function. So by gluing back, I really mean inserting some sort of infinite sum of state between all the seams, and then performing the integration over the rapidity of the particles that I've inserted through the seam, summing over all the possible bound state that I can insert, all these sort of complicated things that are represented here by this scary-looking integral sum sign. OK, all of this can be done, and of course, all these sums will act to some loop order depending on how much length this operator have, and I will refer to these different quantities LA and LB as the 2 bridge lengths. So this is, let me call it the adjacent bridge length, and this is the bottom bridge length. So depending on how big my operator is here, I will have way more connection here, means that actually this particle will have to interact with with more of the physical state, meaning that this will be pushed. Or in a different way, this exponential will become more and more dumped the higher this length are. OK, very well. This is like some sort of schematic idea. And importantly, we see that actually the different contribution that come from this gluing back these 3 different seams actually factorize in the hexagon proposal. OK, very well. So schematically, what I really would like to do is practically what I was trying to explain before. I want to take these 2 things, glue them back. And the first thing that I can do perturbatively is, OK, let me take 3 vacuum state, I can insert them, and I can glue this, and I have I can construct some structure constant to some loop order. If I want to start adding, go higher and higher in the loop order, I will have to, at some point, start inserting particles in one of the edges. And the first one to contribute is the one in the bottom bridge. OK, so I start inserting a particle in this bottom bridge, and I keep on doing this over and over again. And this, in some sort of sense, is how I can construct perturbatively structure constant starting from the hexagon. Very well. I arrive at some point where, unfortunately, some effects come into play, which are called like wrapping effects. You can think of them as some sort of finite size effect. The fact that actually my operator has a finite length is not infinite, so at some point I can have mirror particles here generated, interact with themselves, and then being reabsorbed. So what we did with Benjamin and Artur was actually try to account for all this possible wrapping contribution. This is one of the possible contribution to the bottom bridge. There is another one which actually interpolates between the 3 one, and it was very important to construct this conjecture for how this finite length hexagon should work. And so what we found is that actually there is a natural way of implementing some building blocks from the QSC, which are these transfer matrices. You can think of them as appearing because, OK, you can imagine that I can insert one particle here, then it needs to interact with all the physical state, and how does interaction with physical states is encoded in an integral system, usually through transfer matrices. So this is some naive idea that one can have and how this works. And the point is that, OK, I have 2 different sort of setup of transfer matrices that I can build up. One comes from this adjacent sort of bridge, which are encoded into some, for the expert in the room, SU2/2 non-compact representation. And then this bottom bridge is encoded into this transfer matrix, which actually is SU4/4 compact representation. So what I try to explain with this slide is that, OK, we have some control on how to compute structure constant, mostly at weak coupling through this expansion that I tried to explain. We have control over this finite size effect. We have something that allow us, in principle, to compute structure constant at weak coupling. Okay, very well. But what happens if I want to do things in other regimes? So if I want to go other regimes, as you can imagine, strong coupling is still super complicated because I have to account for more and more of this integral, more and more of this particle, which means that I have to account for more and more of these integrals, more and more of these sums. This becomes a very complicated object really, really fast. So we need to actually think a bit outside the box, or at least learn from what has been done before, for example, the anomalous dimension, to try and figure out how can we overcome this complication and try to use the hexagon to compute things at strong coupling. So, of course, there is a caveat to what I said. You can actually go to the classical string regime where your operator and the spin of your operator is really large. And in their regime, you can actually use, again, integrability of the worldsheet. And this also allows you to study this if you want, seemingly easier strong coupling regime. So what can we do? Well, for the anomalous dimension, I think 11 years ago, 12 years ago, was found that actually if you go, for example, to strong coupling, you can assume that there is a regular expansion of your dimension of your operator, and actually it's a regular expansion. What does it mean, a regular expansion? It means there is a polynomial in S. And if I, for example, try and study how I can solve the problem of the anomalous dimension at small spin, I can see that, for example, I can fix the first order of my expansion at strong coupling by doing a small spin expansion. Okay, this is fantastic. Can we think of doing something similar for the structure constant? Well, we can try. And since, as I mentioned before, we have constructed an ansatz for the structure constant in terms of QSC building blocks, that means that actually we can use all the results that have been found for expanding the anomalous dimension at small spin to actually try and construct things in the structure constant. Again, it's a bit weird to try and do it. It's weird also to try and do it here, but since you have the QSC as a construction, you can do it mathematically in this sense, but it's important. It would be interesting to understand actually what happens to your local operator when you expand it at small spin in some sort of way. Here I'm representing the leading radial trajectory where all my SL2 operators are. So for each, I have one dot at each value of the spin, and they go to infinity. And you see that what I want to do is that I want to expand close to this BPS point. So I want to expand close to S being equal to 0. And OK, I can do it, as I said, in a more mathematical sense, but I don't have a clear field theory interpretation of what does it mean to actually go to this small spin limit. But OK, nevertheless, as I said, I can take the small spin limit for the QSC. So I can think of it as some sort of like a solution. So imagine it that somebody gives you these P functions that come from solving some complicated, well, not so complicated, some QQ relations. And the solution has been found again by Collia and the collaborator up to the second order in spin, which is known as the curvature. And for us, it will only be important we'll only care about the leading order in S, which is called the slope. And so the idea is that, OK, I have all these functions that are given to me by the solution of the QSC. And now I just want to point your attention to the fact that all of these are actually coupling dependent, which means that I have actually control in the small spin limit on actually the expansion through weak and strong coupling. The x here are actually your Zhukovsky variables, which is a canonical way to represent the rapidity or the kinematical value for your state. And OK, epsilon in this case is actually a function of the spin, and we see that all of these scale as something which is square root of spin. And j in here is the length of the operator that I want to study. Again, for the expert in the room, actually at this order, the p and the q are actually proportional to each other because the QAI matrix is actually diagonal. It's diagonal and an identity. OK, very well. What does it mean? Well, as I tried to explain before, in this hexagon formalism, we have more or less 3 building blocks. One is the normalization, which encode the information about the state. I've not talked much about it because actually this is a very complicated object, and people usually try to avoid it. This is written in terms of Fredholm determinant. And as we will see, it will be complicated to try and extend it at small spin, but I will say more about it later. And then we have these 2 bridge contribution. As I said before, there is the bottom bridge, which is the one that I presented as an example of how to construct perturbatively the hexagon. And the other one is the adjacent bridge, which is when I insert mirror particles in one of the 2 adjacent seams. OK. For the sake of simplicity, let me just focus on the bottom bridge. And let me try and understand what happens when I try and plug in this small spin expansion. Well, we have seen from our QSC construction that we can write the contribution from one mirror particle insertion in this way, depending on this transfer matrix. This transfer matrix is constructed by a product of Q function, but they're actually the same, they're the same as the P function. So I can take this function, multiply by themselves, sum over the index, and I need to analytically continue one of them to actually construct this transfer matrix, which practically means sending x to 1 over x. OK, very well. I can do this. I can plug it in, and then I can start seeing what happens. Well, the first thing is that actually, if I want to construct only the leading order in S, I don't have to account for multiple mirror insertion, because all of these are suppressed in higher powers in S. How do I see this? Well, we see that this P scales as square root of S. This is a bilinear object in NS, means that this will scale as S. And OK, how do higher mirror particle insertion look? Well, they will look as product of this integral intertwined with some kernel that will link the two mirror integrations, which means that they will be quadrilinear, sextilinear, and higher order in this P function, which means that it will be suppressed in higher in the small spin limit. So this is one of the first simplification of this small spin, is the fact that actually I only need to account for a single mirror insertion. I don't need to account for multiple mirror insertion. This is a very good news for us, because then we only need to do one integral. And as I mentioned, we have full control over the coupling. So in principle, we're very good. Now the thing is that, of course, you can start asking, OK, what happens about A and N in the small spin limit? Well, A follows from B. You need to do some contour manipulation, which are a bit too technical, but the idea is that there is some relation between the transfer matrices in the SU. The transfer matrix is the build up, the adjacent build in the QSC, and the one build in the bottom. And you can prove that the one appearing practically are the same as small spin. This is some property that is not valid at finite spin, and actually is valid only for the physical shit at finite spin. But anyway, at small spin, I can relate the two transfer matrices, which means that I can rebuild the adjacent in the same way with the same very simple transfer matrices of the bottom one, up to a fact that I need to analytically continue the length of the bridge. So now the length which appear in here will be actually, I will need to insert it in with a negative value. So if I study some integral for some length of this bridge B, which means some combination of the length of my operator, if I want to study the same, for the adjacent, I need to insert minus the length of the adjacent bridge. OK. As I said, what about the normalization? Well, unfortunately, the normalization cannot be, we don't know how to expand it at small spin, because it's as I said, it's a determinant. And the determinant depends, the dimension of the determinant depends on the spin of my solution, which I'm trying to compute the normalization of. This means that if I try to analytically continue a small spin, I need to compute the determinant of an object, which is actually a zero-dimensional one. We don't really know how to do it. So unfortunately, up to now, it seems like we're only able to compute a ratio of two different structure constants. So we need to compute objects, if you want to extract information at small spin, that doesn't have dependence on this n. OK, very well. So what can we do with this integral that we want to study? Well, we can start analyzing it, and we can see that it has a very nice properties. First, let me just do some change of variables. So I have defined x and y that appear in the transfer matrix as some, these are the shifted Zukovsky variables. The index plus a means that I'm shifting plus ai over 2. Minus a seems that I'm shifting u, but minus ai over 2. So I can look at the transfer matrix, and I see that as again, a dependent on the two shifted Zukovsky variables, and also on this ratio of Bessel function, which is something that happens. These are sometimes can be also rewritten as Koch sinh functions. I should stress, and I was a bit skipping over it, this is the solution for even j. There is also an analogous solution for odd j, but the two, once I will arrive to my results, the two will actually, our result will extend to all values of j. OK, very good. So let us look at this integral. Well, first of all, there is this very nice kernel that to people who have done some localization reminds them a bit of localization computation. Where did this came from? Well, at some point where we did this change of variable, we were able to extract all the dependence on this shift A. And in my definition, there is a sum of array. And this sum of array gives me this kernel, which for the people who have done the curvature computation is practically the same as the curvature kernel once you've done some partial derivative. So in some sort of sense, what we see is that computing the structure constant seems to be similar, or at least computing these pieces of the structure constant seem to be similar to computing pieces of the curvature. they have a very similar structure, and the type of integrals that appear are very similar. There is also some other caveats that I should explain, is the fact that actually for the people who know how this t behaves at large values of u, know that it is actually exponentially enhanced. And so you will say, okay, this integral, you cannot compute it. Does that make any sense? Well, you need to add a prescription. This is also true for the hexagon when you compute them at finite spin. And the prescription that we found that would work to match perturbation theory or computation done through from perturbation theory is actually to take some particular cut of the transfer matrix that actually practically drops out this exponential piece. Okay. The last thing that I would like to add is the fact that actually if you try and compute this with A, you see that this A, given the fact that I've put a negative bridge, actually gives you some logarithmic divergences when computing them. So you need to regularize them, and there is some redefinition of this exponential that we can use to actually regularize them and extract the correct result. Very well, so now we are actually equipped to study our weak coupling small spin and see what we can do. Well, actually, we can actually solve this integral for whatever value of j and l that we want. And actually, this is written as an infinite sum of some gamma function and single zeta values. OK, very well. That's very nice. What we did to actually do this, well, we implemented some hidden symmetry that you don't see, but it's very clear from the hexagon picture. The fact that actually the left and the right bridge actually are the same in the sense that they can be intertwined by some change of variable. Very good. OK, well, now we can play. So we can actually plug it into Mathematica, expand it for ones to how many loop orders we want. I think this is 14, just for the sake of it. And of all of this, this is the result for j equal 2 and lb equal 1. And it's the only one that actually I can test against perturbative computation, because I cannot construct a spin a function is spin for higher twist. I don't know what is the basis of function, but in this case I know that are harmonic sums, and so I can then take the small spin limit of these harmonic sums, and I can test that these first two orders are actually compatible with perturbative computation. Very well, OK, so far we've done perturbative computation, very nice. But what can we do with strong coupling? This is what we want to do, and so what can we extract from our result? Well, we now want to study this f of j at strong coupling, and we see that it is useful actually to rewrite it in a way that we've seen from Bersel's talk on Monday, which is in terms of something that really looks like a Tracy-Widom distribution, and maybe this is the case. And also, for people in the audience who have done some integrated Wilson loop computation, the structure of this f of j is very similar to the one of the matrix model coming out of this computation, which may hint at the fact that indeed, when you try and do this small spin limit, you need to use non-local operators to actually express the form of this small spin expansion. Anyway, so OK, this is something that we can study. And actually, what we can do, we can plug it into Mathematica and try to actually expand at leading order in G and try to resum in this N. It's very important to notice that we have an infinite sum in N, and this is actually very bad for us because after the first order in G, we are actually unable to resum. The two things do not commute, and so if we try and do the first G expansion and then sum in N, this doesn't work. The thing is, you get that higher order will contribute and they are enhanced. So what we need to do in principle will be to resum over N and then do the large G expansion. We're not able to do it, so we actually have to go and use numerics. So how do the numerics work? Well, let me just simply say you're plugging in some values of G. In this case, it's easier to work with G and not with lambda, that we will use later on. And G is, again, the top coupling, and lambda is the top coupling. And at some point, you want to plug in different values of G, interpolate with basis of function that you guess from the analytic expansion, and then, of course, some basis of variables. And as I mentioned, you can do this. You can plug it in. We have a full solution. We know everything. And you do it for different values of L to some precision of 20, 30 digits, and then you try and reconstruct what are the values of this coefficient. OK, for example, these are some results for j equal 2 and different values of the B bridge. OK, but we see that actually there is an overall structure into this result, which is the fact that actually we can see that there is a bit which depends on the anomalous dimension expanded as small spin plus some polygamma functions. and some logarithmic depending on lambda. And there is a bit which is almost polynomial. There is a pole in 1/j in the adjacent bridge, but this is expected from the fact that the adjacent doesn't have a nice limit for j going to 0. And we know that this thing depends on, this is only depending on the j, l, and the zeta values. Okay, very well. What does this tell us? Well, since these are psi function, we know that they may come from some expansion of gamma function. So what we can do is that we can cook up, based also some previous result by Benjamin and Del Young, some, let me say, finite spin representation for the bottom and the adjacent bridge in terms of the quantities that appear. So in this sense, this is a strong coupling expansion that we believe should be valid also at finite spin. Of course, we cannot prove it, but it's a natural extension based on results coming from this BMN limit studied in the literature. And if we take this and expand it at small spin, we see that actually we can, of course, reconstruct the results from before. And the important bit is actually to notice that we have to practically, there are these two pieces, dB and dA, that seems to admit some nice expansion in the spin. Again, in this case, of course, I'm still doing small spin, so this dB, I only know up to leading order in spin, but I know that this is polynomial bit in terms of j. So there seems that I've managed to encapsulate all the difficult contribution that come, then these non-analytical bits into these prefactors, and I have managed to find some sort of nicer object that I can study. Okay, very well. So far, what have I done? I've tried to construct the small spin expansion for the hexagons. I have seen that I can study this at weak and strong coupling, and at strong coupling, I found this very nice form. Okay, this is very tantalizing, and you think like, okay, maybe I can actually make some bold conjecture. As we heard from Benjamin, conjectures are for free. So I can think of, okay, maybe this nice structure, actually, it's also there for the norm. And I can think of some sort of way of encapsulating all the complicated bit of my structure constants, all these non-analytic dependence on the quantum numbers, in some prefactor that I can think of it in two different bits, one that depends only on the R charges and one that depends on the ADS quantum numbers, which are the dimension and the spin of the operator. And these two encapsulate all the complicated analytical part, non-analytical behavior in spin of the structure constant. And then I'm left with this reduced structure constant D, which depends on the different charges of my operators, and also the spin S. But as we've seen, we know that, okay, from normalization, we can see that D has to go to 1 at leading order. But we know that we can make some sort of assumption following what has been done for the anomalous dimension that maybe this log of D, as we have seen from the small spin, may admit a regular expansion on small spin. What do I mean by regular expansion? I mean that this is actually fully a polynomial in S. And each term of this S expansion is itself, a coupling-dependent quantity. But all of this actually is very nice because at this point, I can, of course, continue expanding at small spin and higher order to fix this coefficient. But I can also study different regimes of my structure constant. And this DJ naturally interpolates between these different regimes because it's a very nice analytical form. And I think similar object was also presented in Frank's talk is that we had to renormalize differently because we really want that our D is, has a very nice irregular expansion. This is fundamental for us because otherwise we're not able to fix this D by studying different limits. Okay, very well. So we have this conjecture, which is, based on our results at small spin and also some other results in the literature. Okay, and now the game, what it is? Well, we want to see how much we can fix of this D. So there is another, ace on our hand, which is actually trying to study this classical string regime. And what does the classical string regime give you? Practically, it allows you to fix all the terms in this D expansion of this Sn plus 1 square root of lambda of n. And we can do this for several orders. And what does this classical string practically thing is the fact that at this point, I'm solving like a minimal surface area problem in ADS. And what are the extremal of this thing? Well, there is 2 point-like strings that represent my BPS operator, and then there's this classical string, which is practically my states once I take the coupling and the spin to go to infinity, leaving the coupling and the spin to be fixed. Of course, I want to expand this in some other regime, which is when I take this redefined quantities to be small. I can do this because my D is a very nice function. And I want to add that actually as we will see, the pole in 1/j, okay, it's not shown in the classical string. It's subleading, but we will see that actually it cancels with some computation in the norm. And I want to add that the norm actually we can study in this classical string regime in the small spin expansion without in the short string regime, which means that actually we can check that our conjecture is valid. Okay, very well. So now we have everything, and let's just see what we can do with all the tools that we have. Well, we can fix actually D up to 2 loop, which is I think so far, if I'm not mistaken, the state of the art. And we can do this by using a mix of our classical and small spin expansion. Once again, I'm doing this for these leading ridge operators, where I then now, of course, I'm beyond the small spin limit. So this is a finite spin result. I want to stress on this. We have used the small spin, which is these purple ones, and the classical limit to fix this coefficient. But this result is valid for whatever value of S you plug in. And this J vector is practically a combination of J1 plus J2, which are the R charges of these two operators. Very well. Okay, there is a caveat, as we see in my fix. The fact that actually we cannot fix this S2 because it's beyond our capabilities with this 2 regime, but we could fix it by checking a comparison with the 2-2-2 result. And we know from the classical limit that there cannot be no J dependence in this coefficient, because otherwise we will see it in the semi-classical, in the classical string regime. I also want to point out that this first correction is actually universal, meaning that this object is valid, it's independent on all their charges, which means that once I factor out all the gamma functions, I am left with something that is completely independent and is valid for all possible operators. Very well, so this goes me to my conclusion. So I hopefully presented some, by now extensively tested, conjecture for computing the structure constant using this hexagon formalism, also in the short operator, for short operators. I have somehow show you that actually we can probe using the fact that we have a QSC-based formalism or the regime, like for example this small spin regime, and actually by merging this small spin regime with the classical limit, we're able actually to probe the structure constant at strong coupling, which it's very nice and good. So then let me leave you with some outlook. Okay, the idea is that can we maybe push this to other regimes, large spins, subleading trajectories? I don't know. It would be interesting to connect this to some SOV-like representation, as we will see from Carlos on Friday. And what happens? Can we do beyond leading end? There were a lot of approximation that I had to do to actually be able to compute the different adjacent bridges in small spin. Will this work at higher order in spin? Can actually we derive some small spin representation for this end? Can we finally be able to do the norm also at small spin? So fix this Fredholm determinant to small spin limit. And also it's very interesting and a bit outside of integrability, but it was very nice maybe to understand if actually the operators what happens to the operator in the small spin limit, and if actually one can think of them from some light array operator. Before finishing, I would like to say that this is 20 years of IGST, and so I was very taken and wrote some nice poem about it. Well, not exactly wrote myself. I used ChatGPT, but you can actually ask it to do many things for which spell IGST in the first line. Anyway, with this I finish. Thank you.
This is the question in the back of the room.
Sorry, I cannot hear you. Can you speak a bit loud there? Yes. Yeah. Yes, exactly. So this is done through Fernando. So what we did, we took our reduced structure constant, we applied it to Fernando result, and we checked that all this number match with our result, and we saw that, and we could extract this. So the two actually match with between the two different approaches.
There's another question by Julius.
Can you comment more on extending to subleading trajectories so you don't have a near BPS expansion? Is that?
Yeah, that would be complicated. I don't know if this. Yeah. Yeah. Sorry. What did you say? There are no BPS operators on the subleading. What did you? Yeah. So it would be difficult. I think it would be as complicated as trying to expand close to one of these points, which are Yeah. The nice thing about this is that you're expanding something which is some sort of vacuum. So.
But then we can use Andrea and friends trick, no? Take the subleading, do Reggie bridges, and make it go to the leading trajectory.
I should add that whatever you want to do, it may interfere greatly with the fact that you can do this integral. This integral can be done in this regime because we know the prescription for doing it, because we could also match it with perturbation theory and guess what was the correct prescription. But we don't know in general how to do this. Even at a large spin, it could be that we cannot actually perform the integration. There is some problem. You know that this T function scale as u to the s. So, okay, yeah. For small s, makes sense that you can do it, but for large s, okay, who knows if you can actually do.
Yeah. Collier?
Very nice. So could I ask, so in terms of, I understood that you use pieces of QC to resum wrapping corrections, right?
Yeah.
In the hexagon format. But
yeah.
at the same time, I think leading S term for the spectrum is actually doesn't contain wrapping in n equals forward, and in BGM it does contain. So to which extent you actually probe your construction with Benjamin, or you can use just bare hexagons without?
So, so there is, I should cross-check this. This is what I remember, but I do remember at some point there is some bit that you can think of it being if you want. It's not exactly true. So it's true that in the large S you're only probing this ABA sort of regime, like this easier bit, but there's still wrapping inside on this. It's wrapping, I think, in a different sense. You have this single mirror excitation, but of course you have all the possible renormalization of the operator on the outside. I mean, I think there is some bits, but Benjamin can maybe contradict me. I think at 5 loops, if I remember correctly, you would see that there is a bit which only starts at 5 loop, which is where you expect the first, this effect to come into play. So even when you construct this object, which is the transfer matrix, you see that there is a bit which is, start from 2 loop and goes whatever you want. And there is another bit which seems to be only 5 loop and over. So you can think of it as some sort of, in the same way as you see the wrapping in the canonical hexagon. But I don't have any more intuition about this. Yeah. 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 Yeah, that's true. So there is this secondary wrapping that you need to account for, which is suppressed, usually at coupling, come into play at 5 loops. And you need it to actually construct this compact T transfer matrices, which means that if you want to do it with a compact T, you would miss half of the answer up to 5 loops. So it would work only to so. So that one probably doesn't account, but this is another type of wrapping that you need to account for. So there are 2 different. Yeah, that one will be at higher order, and you would need to care for it. But indeed, sorry, there is this secondary wrapping, which is like this subleading wave that you have. Sure, yeah.
Okay, last question.
Can you show the slide with the huge data? Yes. So how do you get this? It's like writing these structure constants like these harmonic sums, and then just in S to 0 or something?
Oh, yeah. So you need to do something very annoying, which is do a lot of spin, interpolate with a basis of harmonic sums, and then take the limit of the harmonic sums for S that goes to 0.
Yeah, about that, I think on this work of Pedro and Alexandre, when they were trying to do that for twist 3 at least, which I think this is twist 2, right? This data or no?
Yeah.
But when they were trying to do that for twist 3, this naive analytic continuation, let's say, was not the ones that they were finding when they were trying to analytic continue in spin. So, but it works for twist 2, but I don't know.
Okay, I mean, I would not even know what is the basis of function to use for twist 3. I mean, some of them you can, but...
they were doing some one-loop stuff there.
Okay, interesting.
Okay, so let's thank Alessandro again.